Let me thank everyone for coming, and in particular Youssef Marzouk for giving a talk about dimensional reduction in nonlinear Bayesian inverse problems. So Youssef is an expert on uncertainty quantification and also Bayesian calculation in complex physical systems. So we're very happy to have you here today, Youssef. So please, the podium is yours.
Okay. Thank you very much, Newt and Katya, for the invitation. It's nice to speak in this distinguished seminar series, very relevant to a lot of things that I've been interested in for a long time. So in the talk today, I want to talk about kind of a broad line of work on dimension reduction, focusing on inverse problems in the Bayesian setting, and in particular focusing on nonlinear inverse problems in the Bayesian setting. And there's a lot of interesting, I think, sort of notions of dimension reduction that one can develop, and there's a lot of, I think, interesting future work that one could, that would be really, good to pursue along these lines. So maybe, hopefully it could stimulate some interest in these directions. Before I kind of get into the details, I want to kind of acknowledge my main collaborators in this work. So this has been, I sort of had work that had many parents, but most recently Ricardo Baptista, former PhD student who's now at Caltech, and actually en route to University of Toronto. Michael Brennan, former PhD student who is now in industry. Matt Lee is a postdoc with me at MIT, and Olivier Zam is a former postdoc who is now at INRIA in Grenoble. And we've all been collaborating, quite actively in these directions, and along with some people that I'll mention in earlier papers that will come up in the talk. So, inverse problems in the Bayesian setting. So I realize, so some of the talks in the series are not Bayesian and some of the talks are Bayesian, but just to kind of, set the Bayesian setting, this is a picture of a satellite remote sensing problem that was actually, this is from a paper by Heikki Harjo and others at the Finnish Meteorological Institute, where the idea here is essentially kind of a tomography of the atmosphere. The goal is to learn the atmosphere, the concentrations of certain atmospheric trace gases as a function of height, and the measurement process is what's called star occultation. So basically, starlight is absorbed by the atmosphere, and the satellite, goes around the Earth, and depending on the position of the satellite, you will encounter more or less of the atmosphere, and you'll measure an absorption spectra. So by sort of comparing starlight that's been absorbed by different amounts of the atmosphere, you can start to build, you kind of create these tomographic measurements, and you can build, try to reconstruct the vertical profiles of concentration for several gases. And this essentially models the Earth like an onion, and so on and so forth. Now, I'm not going to get into the details of this whole process. I just want to use this to motivate, essentially writing the inverse problem in the Bayesian setting. So here, X is the parameters we're trying to invert for. Those are the atmospheric concentrations as a function of altitude. And Y are the spectra that we're going to invert from, the things we're going to condition on. And in the Bayesian setting, the essential idea is that I want to write the posterior distribution of X conditioned on the observations Y. Here, I'm just writing the posterior density, and it's proportional to a likelihood function here, viewing this as a function of X, and a prior density. And a lot of modeling goes into how do you pick these priors. The likelihood function contains a forward model that's a model of sort of atmospheric transmission or absorption using Beer's law. But you put these things together, and the goal now, the sort of computational problem, becomes one of how do I characterize the posterior? So how do I actually draw samples from this distribution, whose density I know up to normalizing constant, for some realization of Y that I'll call Y star. And the computational challenges that one faces when you put inverse problems in the Bayesian setting is, okay, in general, this posterior distribution is going to be non-Gaussian because either the prior or the conditional density of the data are not Gaussian. X usually represents the discretization of some, in principle, infinite dimensional thing. It's really, say, a function of altitude that I'm trying to recover, but I might discretize this at a large number of points. And maybe evaluations of the forward model and hence the likelihood, which is really, I'm just thinking of this conditional density holding the data constant. This is the likelihood function. They may be expensive because the forward model is embedded inside of that. So these are kind of the standard computational challenges. And my claim is that if you could find and exploit some kind of low dimensional structure in this problem, then whatever your favorite method for sampling the posterior, whether it's MCMC, whether it's some sort of measure transport, whether it's some variational approximation, is generally going to be aided by some low-dimensional structure. So in the talk, I'm actually not going to sort of focus on one specific computational method. I'm sort of trying to solve this outer problem of how do we, identify low-dimensional structure? What do I even mean by low-dimensional structure? And how can we detect it? And we'll talk a little bit how you might then exploit this low-dimensional structure in algorithms. So in particular, I'm going to talk about sort of two notions of low-dimensional structure. And I say this is non-exhaustive because I'm certain there are more notions of low-dimensional structure that one can devise. But I'll just focus on these two. And the two are as follows. Essentially, the idea is that the posterior distribution of the parameters x could be well approximated in possibly both senses. One is to say that the posterior is somehow a low-dimensional update of some dominating reference measure. Maybe the reference measure is the prior, but maybe it's also something else. Or maybe the other sort of low dimensionality is maybe I take the variables that I condition on, meaning the observations, and project them into a subspace or find some other low dimensional summary of the data. And that I could do so without incurring too much error in my approximation to the posterior. So both of these notions of low dimensional structure involve approximating the posterior by something else that's somehow easier to deal with. And our hope is to understand the approximation error and control it and kind of identify settings in which the approximation error might be small or acceptable enough to the user. So that's kind of the idea. What we'll begin with is actually, I said I'll talk about nonlinear problems, which is really going to be the focus of the talk, but I want to begin with the linear Gaussian case because it actually provides a lot of good intuition. And this is a case where we can essentially write down everything and understand it pretty well. So I'll begin with the linear Gaussian case, and then we'll go to kind of the more challenging nonlinear case. And by the way, if anyone has questions anywhere along the way, just let me know, interrupt. I don't think I can sort of see the chat, but just speak up, and that will be the easiest. So let's begin with the linear Gaussian inverse problem. So I mean, as you all know, sort of the linear Gaussian inverse problem here, again, my parameters are x, my observations are y. G is the forward operator, and here, let's just think of it as finite dimensional. So this is basically some matrix. I have additive Gaussian noise epsilon with this covariance that I'm writing as gamma y given x. I endow x with the prior that's also Gaussian. So here's the prior mean, and here's the prior covariance. And of course, the noise and the parameter are assumed independent. So in this setting, you could write down the posterior. It's again Gaussian, and the covariance is essentially, you can write the inverse of the covariance of the precision is essentially the Hessian of the log likelihood. That's what this term is. And then this is the precision matrix of the prior. You add those things together, and the inverse then gives you the posterior covariance. So this is sort of well known in just algebra. Now, my claim here is that you can understand low dimensional structure in this problem through essentially looking at certain eigenproblems, and in particular the generalized eigenproblems. But there's some intuition behind what these eigenproblems actually involve. And I can classify these eigenproblems into two. One involve matrix pencils that are of the dimension of the parameters. That's this first row. And the other one involves matrix pencils that are of the dimension of the data. And what are these things? So in the parameter space, I could, for instance, compare the Hessian of the log likelihood. That's this G transpose, observation precision G, and the precision of the prior. So I could compare these two objects. But almost equivalently, I can compare the prior covariance and the posterior covariance, or I can compare essentially the difference between the prior and the posterior covariance to the posterior covariance. So essentially, the second norm, the second matrix in this matrix pencil is just kind of giving you the norm in which you decide to look at things. But all of these essentially have common eigenvalues and relatively simple transformations between the eigendirections. I could equivalently look at the data space. So now these are matrices that are the size of the data. If the data are m-dimensional, then these are m by m matrices. And there's kind of analogous to these two matrix pencils in the parameter space. These are the data space pencils. And essentially this says, let me compare the marginal covariance of the data with the noise. Or let me compare just let me subtract out the difference. And these again have common eigenvalues. Well, they differ by a factor of 1. They differ by 1. And maybe one way of bringing this all together is to think about the forward operator and kind of whitening it. On one side, I could use the square root of the prior covariance, and on the other side, I could use the square root of the noise precision. And I could look at the left singular vectors, and I could look at the right singular vectors, and I can relate those to essentially the eigenvectors of these matrix pencils and the eigenvectors associated with these matrix pencils. So these are just different ways of essentially capturing in what sense do the data inform me relative to the noise, and in what sense does the prior differ from the posterior? I mean, if I think about this, for instance, is maybe quite intuitive. I'm essentially trying to find directions in which the posterior contracts most relative to the prior. So in a relative sense, then the eigenvalues of this matrix pencil then essentially capture this relative sense of contraction. And okay, so these have been pretty well analyzed, and they actually can give rise to optimal low dimensional approximations in particular senses. So let's focus on the first notion of low dimensionality, which is to say that the posterior is some sort of low dimensional update of the prior. If I consider approximations of the posterior covariance matrix that essentially are low rank updates of the prior covariance, like I say, this is the approximation class that I want to consider. So I constrain the rank of this update to be R or less. And I consider loss functions between symmetric positive definite matrices. And there's many loss functions we can consider. You could consider sort of the natural geodesic distance on the manifold of SPD matrices. I could also consider KL between Gaussians that have a common mean and these two different matrices. If I now say, okay, if I want to minimize loss functions in this class, over this class of posterior approximations of the posterior covariance, then basically the minimizers for any set of loss functions in the class that's defined in this paper has the following form. Essentially, this comes from essentially the generalized eigenvectors of this particular matrix pencil. And these are the generalized eigenvalues lambda. Okay. So this gives me optimal approximations of the posterior covariance as a rank R update of the prior covariance. And you can then interpret these directions as somehow the most informed, or the directions in which the variance of the posterior is most reduced relative to the marginal variance in that direction under the prior. And okay, and then similarly, if I care about approximating the posterior mean, that's the other part of the posterior I need to care about, you can similarly find essentially a rank R matrix that you apply to the data that among all rank R matrices minimizes, say, this Bayes risk. So here's my estimate of the posterior mean. Here's the true parameter. I minimize this squared loss in expectation, and the loss is weighted by the posterior precision. So I'm summarizing kind of, a lot of detail in this paper, but the idea is that I can look at certain eigenproblems and capture this notion that the posterior departs from the prior in a subspace, or that is well approximated by a distribution that departs from the prior in a subspace. So, okay, similarly, I could kind of look at the dual of this problem and say I could also project the data. And similarly, and so there's this paper by Giraldi and others that say basically if I want to find a R-dimensional projection of the data, I'm going to like this, and that maximizes mutual information, and you can also say this kind of then maximizes a certain KL divergence on average, that this again comes from leading eigendirections of one of the matrix pencils that I showed you 2 slides ago. Okay, so this is kind of optimal, like information preserving projections of the data. If I want to preserve as much information as I can, this curly I here is the mutual information, then these eigenproblems tell me how to project the data. Okay. And there's extensions of this to say, okay, what if I don't really care about X? I care about some, linear transformation of X. And again, I can think about this as kind of a goal-oriented setting. So I don't really care about X as the inversion parameters. I care about some Z. I could write approximations of the posterior covariance of Z as low-rank updates of the prior covariance of Z, of gamma Z. And I could also find informative low-dimensional projections of the data. So that's all well and good in the linear Gaussian case. Now, any questions there before I kind of switch to the nonlinear setting? Okay. Yeah. So the idea here, now I'm going to get into much more detail about how we kind of take these ideas, these notional ideas of projecting data or looking for low dimensional subspaces of the parameter space and bring that to nonlinear problems. So what do I mean by nonlinear inverse problems? So nonlinear forward models or certain non-Gaussian priors. And many things change once you go to the nonlinear case. So rather than saying my only things I care about are the mean and the covariance, now I have whole distributions. Like I can't just parameterize things by mean and covariance. The Hessian of the log likelihood now depends on the parameters. It's position dependent. So everything becomes much more complicated. The geometry of the posterior kind of locally can change. And also the shape of the posterior depends on the realized value of the data. We don't have this nice thing that in the linear Gaussian setting, the posterior covariance is independent of the data. In the nonlinear setting, well, everything depends on the data. So I'll say at the outset that in this setting, optimal approximation is hard to achieve. It may be more than we may be able to do in general. So we're going to be a little more modest and aim for a notion of controlled approximation and hope that that performs well in practice. So what do I mean by that? So let us come back to this first notion of low dimensionality, which is that, again, as we saw in the linear Gaussian case, the target distribution might be well approximated as some kind of low dimensional update of a dominating reference measure. What is that dominating reference measure? Well, the standard thing to think of would be the prior. And this again says that the posterior somehow involves changing from the prior maybe only in one direction or much more in one direction than in another. And this idea has been floating around. It goes under different names. Likelihood informed subspaces is one, but many kind of flavors of this. Why would we expect this in inverse problems? Well, in general, the forward operator is sort of smoothing. I might have an informative prior. I have finite amounts of data. So somehow there are aspects of the parameters or modes in the parameter space that I expect not to be able to learn much about. And the more ill-posed the problem is in the classical sense, the more I expect this to be true. The less sort of, the more smoothing the forward operator is, the more I expect that, for instance, like high frequency aspects of X are not going to change much from prior to posterior. So ill-posedness is kind of our friend in that this is going to give rise to more accurate low dimensional approximations, more opportunity for dimension reduction. So let's consider a certain approximation format for the posterior distribution and explore how we can actually find good approximations in this format. So let's consider on the top line here the original posterior density. And here I'm just going to drop y for notational convenience for now. Just think of pi as my posterior density function. Rho, think of that as the prior, and curly L is the likelihood. And let the parameters x live in Rd. Now I want to consider approximations that are of the format I have here on the second line. So pi tilde r means an approximation of the posterior that is essentially an r-dimensional update of the prior. So the prior here is intact. And then I have essentially a projection of my parameters x onto some r-dimensional subspace. Comes from this given by this matrix UR. And I have a low dimensional sort of replacement for the likelihood. This L tilde R is now a function from R little r to R plus. Okay, so I could think of this as like a profile function. I'm going to replace the standard likelihood, which is a function from Rd to R plus, with this R function from R little r to R plus. And now the things that I need to choose in this approximation format are essentially the matrix UR and the function L tilde R. Okay, and I want to do this in a way so that the approximation error is controlled. In other words, I want to be able to say, okay, for some R, for some desired error epsilon, and some notion of divergence between probability measures, I would like to find an approximation in this format for some R that depends on epsilon that achieves this error bound. Okay. And there are many choices here. In a recent paper, we kind of talk about this in general for alpha divergences, so that includes Hellinger distance. But in this talk, I'm just going to focus on KL. So in particular, forward KL divergence. Okay. So I want to find an approximation where essentially I want to control the forward KL to some level epsilon, and I want to be able to pick R accordingly. And of course, then pick L tilde R and pick UR accordingly. So how do I do this? So the first thing we kind of want to do is to think about how do this projection UR, so the sort of the subspace that I'm going to pick, where I update the prior, and L tilde R, which tells me essentially the shape, the way in which I update the prior, sort of the shape on that subspace, the shape of the posterior in that subspace. How do these two errors decompose? So if I have KL divergence from my original posterior to my approximation pi tilde R in this format, I can actually break it up exactly into the sum of two terms, pi to this pi star R and then pi star R to pi tilde R, where pi star R involves essentially replacing the likelihood function with a conditional expectation. So maybe to kind of make this more clear, it's a kind of, Pythagorean-like identity where, this is exact. So how to put this, basically, the first term here corresponds to the bottom leg of this triangle, and it's a function only of UR, of the subspace. And then the vertical leg of this triangle corresponds to the second term, which is a function of the subspace and the L tilde R. Now, what is this pi star R? Essentially, it says, okay, let me replace the likelihood with the R-dimensional profile function that involves, so no, I need an X here. I apologize, I need an X here. But basically, the expectation of the likelihood over all the directions that are orthogonal to the range of UR. So in other words, the likelihood function might be not entirely flat outside of this R-dimensional subspace, but I'm just going to replace it with the expectation in those complementary directions. So if I pick my pi tilde R to be pi star R, in other words, if I pick pi tilde R to be this, then I can essentially make this leg disappear. I can make this vertical leg disappear. And then all I need to do is worry about this term of the approximation error, which is a function only of the chosen subspace. So this is to say I can really pursue the approximation in two parts. Given any subspace, I know how to pick the optimal profile function. So let's just say I do that. And now let me focus my attention on how do I pick a good subspace. So, okay. So yeah, this is kind of what I just said. Choose the optimal profile function to send this term to 0, and then pick the UR that minimizes the first term of the error. So, as I said,
Youssef, can I ask a question? What's the condition for the decomposition? I think it's not for any pi r star, right? Maybe didn't get it.
For this decomposition to hold?
Yeah.
So this is exactly true as long as we have KL divergence. It becomes more complicated if you don't have KL divergence, but it's for this specific pi r star. So here I'm defining pi r star to be this. Yeah.
Yes. Thanks.
Yeah. Okay. Right. So yeah. In other words, like otherwise in general it's like a triangle inequality, but if for the specific pi r star it's equality. That's the point. Okay. So I want to construct an upper bound now on this KL divergence from my original posterior to essentially the best approximation that is of the form of an R-dimensional update of the prior. That's what this pi r star is. And to construct this upper bound, I'm actually going to have to make an assumption about the prior, interestingly, and not the likelihood. And the assumption on the prior is that it satisfies a log Sobolev inequality. So that's essentially going to be our kind of working setting, and this is a kind of this is basically how non-Gaussian things can be. So we cannot be arbitrarily non-Gaussian. We cannot have tails that are too heavy. But if the prior is sufficiently close to Gaussian in the sense of satisfying an LSI, then all this machinery is going to work. But this includes in some sense a relatively interesting class of priors. Gaussians, uniform and compact and convex domains, but also Gaussian mixtures. Because they're bounded perturbations of Gaussians, push forward the Gaussian by Lipschitz function. So various things that you could do that encompass non-Gaussian priors. Okay. So under those conditions, we can write kind of an LSI, and for simplicity, I'm just going to consider a standard Gaussian prior. You could make this all more general to an arbitrary Gaussian prior. But let's just consider a Gaussian prior with identity covariance. So here's the LSI, which essentially controls the entropy of some test function in terms of its derivatives. And now if I choose this function f to be the likelihood, then what I can do is essentially bound the KL divergence from the prior to the posterior by the expected outer product of gradients of this likelihood. Okay. And or essentially this term here. Now, how what am I going to do with this? basically, what we're able to show in this paper with Olivier is that I can take this log Sobolev inequality and consider it in subspaces. So rather than, you can think of this as sort of like the zero-dimensional update of the prior, where I'm updating absolutely nothing, and so I'm looking at the KL divergence from the posterior to the prior. But now let's say I start to update rho in a subspace of dimension R. Then essentially I can bound and let the update specifically be given by my pi R star. Then essentially we can bound above and below the KL divergence in terms of a quantity that comes out of the LSI. It's this expected outer product of gradients of the log likelihood. And essentially now for any subspace, so this is for any subspace UR, for any, well, I'm assuming that this matrix here has orthonormal columns, but for any subspace given by the range of UR, I can control the KL divergence above by essentially what is missing in the trace of this diagnostic matrix H. So to kind of set things, H I can think of as, I call it a diagnostic matrix. This is a D by D matrix if the parameters are D-dimensional. It's really kind of a relative Fisher information matrix. I'm looking at the gradient of the log likelihood, outer product with itself, and I'm taking the expectation over the posterior. Now, why the expectation of the posterior is in itself challenging, but let's just go with this for now. If I take this expectation of the posterior, I construct this diagnostic matrix. For any subspace that comes along, I can tell you an upper bound on the error of this KL divergence, but moreover, I can minimize this upper bound. Because how do I minimize this upper bound? I essentially need to look at eigendirections of H. So this is basically, if I take the leading eigendirections of H, then you can see that I can basically minimize this upper bound for any R, and what's left over then is the sum of the trailing eigenvalues of this diagnostic matrix H. And this is now a controlled error. And I want to emphasize like this, there's no unknown constant here because I'm using standard Gaussian prior, so the LSI constant is 1. So this is literally the forward KL divergence from pi to its best approximation in the format of R-dimensional updates of the prior. And if I pick UR to be the leading eigendirection of this diagnostic matrix, then I have this error bound that comes from the trailing eigenvalues. So this is useful because now we've kind of taken a kind of intractable problem of how do I minimize this over UR and said, okay, I'm just going to minimize this upper bound, which is tractable. And so let's see how it works. Let me come back to the example that I started with, which is this kind of atmospheric remote sensing example. We have a Gaussian prior on the vertical concentrations of the gases, and we discretize, some relatively reasonable discretization dimension here up to P200. And I'm going to show you basically the actual KL divergence that we computed numerically, laboriously, versus the error bound. So here's the diagnostic matrix that I had before, outer product of the gradient of log likelihoods integrated over the prior. Here's the error bound, and here's the actual KL divergence that's achieved for some particular realization of the data Y. And what you could imagine doing is, okay, like this is the diagnostic matrix, so this is kind of, shows that we have this sort of, the bound works, the theory works. We didn't get to this immediately. There have been sort of related attempts in the literature and in some of our work as well, where we tried averaging over other measures. So now let's consider a diagnostic matrix that again takes the outer product of the gradients of the log likelihood, but averages it over some other measure that I call nu. What if nu is the prior? Well, I get this error here. What if nu is a Laplace approximation of pi? So kind of local Gaussian approximation of pi of the posterior center around the map. And you can see we don't do quite as well. And I could do the same thing. Okay, what if I now, instead of doing that, this is something else that's been done in the literature. This is formally what's called likelihood-informed subspaces. Let me take the Hessian of the log likelihood, which is a function of the parameters x, and average that over a different nu, where nu could be the posterior, it could be the prior, it could be a Laplace approximation of the posterior. And you can see you get some sort of intermediate error. The averaging the Hessian of the log likelihood over the prior gives you a reasonable subspace as well. But the best that we find here empirically is the one that comes from taking the leading eigendirections of this guy, of the diagnostic matrix that we proposed. So yeah, and you can look at the same thing in Hollander distance and so forth. So okay, so this is well good. So this is kind of saying that this diagnostic matrix seems to give us both a good approximation in the sense of KL divergence and an error bound for that approximation as well. And you can see, okay, it's what was ostensibly a 200-dimensional problem. You can drive that, you can essentially come up with an approximation of, KL divergence that's on the order of 10 to the minus 4 in something like 45 dimensions, something like that. Yeah, so there is dimension reduction to be had in this problem. But in general, we have a diagnostic for the dimension reduction because you could compute the eigenvalues of this diagnostic matrix and just see how quickly they decay. Okay, so that's well and good. Now, how to actually use the subspace and the posterior approximation that depends on that subspace in practice. So this is, again, kind of the format of our approximation. And, well, what can you do? So, I mean, one natural thing is to say, let me come up with MCMC algorithms that just directly target this approximation. And those MCMC algorithms are morally R-dimensional MCMC algorithms rather than D-dimensional MCMC algorithms, because essentially the only interesting part of this distribution is the part where you modify the prior according to L tilde R. Everything else is, this is the interesting part. And then the remaining directions are conditionally distributed according to the prior. So as long as I get sample from this conditional prior, then I can sample from this approximation up here. Essentially, I can sort of fill in these U perp X directions like this. Now you might say, okay, how do I calculate this optimal profile function, which is itself a conditional expectation? Here you could use pseudo-marginal methods, or you can do some further approximations. And there's several papers here. Tiangan Cui did a lot of work on this in collaboration with myself, and then, in subsequent, a lot of work in collaboration with others, devising different MCMC algorithms for these kinds of problems. Another thing you might imagine, if you like methods like measure transport, so essentially like normalizing flows or variational approximations that say, I'm going to represent the posterior as the push forward of some reference measure under some transport map. Essentially what this says is that I can construct a map that pushes forward the prior to the posterior, or to this approximation of the posterior, that departs from the identity only on an R-dimensional subspace. So this map is somehow lazy in that it is non-identity in R directions and identity in the remaining D minus R directions. So the problem of finding like a mapping from RD to RD is really shrunk to a problem of finding a mapping from R little r to R little r. So that's, a way of using the dimension reduction. Now, another kind of computational issue is, well, this diagnostic matrix that we like involves an expectation of the posterior. And, well, how do I deal with that if the posterior is the thing I'm trying to approximate in the first place? And so many algorithms have been proposed, but in general, they have some notion of iteration. What you could really do is imagine, constructing a diagnostic matrix first based on some other distribution, maybe the prior, finding the leading eigendirections of that matrix, constructing an approximation of the posterior based on that subspace, which is not optimal, and then sampling from that, constructing a better diagnostic matrix, solving the eigenproblem, getting a new subspace, sampling from that, and then iterating your way there. So this is essentially saying, okay, start from some other measure in this diagnostic here, but sample from things that will gradually approach pi tilde r. Now, I don't have any kind of theory that guarantees this thing is going to converge, to be clear, but empirically this seems to work in many problems. You could do this in different ways. You could fix an error threshold and use that to pick the rank. And so if I begin with the prior, I find a subspace, and maybe at the first subspace, I don't achieve the error threshold, but then I do. And essentially the subspace kind of evolves. The red is the error bound, and then the blue is the error bound, and the red is the actual achieved error, or at least some empirical approximation of the scale divergence. And you can see this is for a different problem. The rank here hovers around 35, or I could fix the rank and just say, give me the best subspace that you can, given your particular diagnostic matrix, and then hope that you eventually achieve some desired error. The error does settle down in this way. So different ways that one can iterate in this way. So, okay, what we've talked about so far is sort of aiming at a specific posterior distribution. How do I approximate it? It's for a specific realization of the data. How do I approximate it as an R-dimensional update of the prior? and how do I find that subspace in which the approximation lives. So to be clear, this is linear dimension reduction, and the core problem is to essentially form this diagnostic matrix and solve an eigenproblem, and then find the subspace. Now, one way of getting rid of this sort of annoying aspect of having to integrate over the posterior is actually to consider a slightly different problem, which is to say, I don't want to control the error in the posterior for specific realization of the data. What if I care about a more relaxed but kind of more general version of the problem, which is to say, let me control the error between my low dimensional approximation of the posterior and the true posterior on average over the data. So what do I mean by that? I mean, okay, here's my pi star. It depends on the subspace. Here's the forward KL divergence from the posterior to its approximation. But now let me say, in expectation over the data, let this error be controlled by some epsilon. Now, it turns out this actually has a lot of interesting links to, you can massage this sort of expected KL divergence into mutual information terms. And this actually has links to some of the, not just the parameter projection, but the data projection that I talked about in the linear Gaussian case. So this expected KL divergence, I can essentially write as the difference between the mutual information of x and y and the mutual information between an r-dimensional projection of x and y. Okay. And you can imagine that somehow, like, you know, if the, you know, if y only informs the, you know, exactly informs only r sort of an r-dimensional subspace of x, then this difference could actually be 0, in which case my approximation would be exact on average over the data. So this really lends itself to the further step of, let us not just worry about projecting the parameters, let us also think about projecting the data and try to solve both of those problems simultaneously. So let me introduce this now kind of further step, which is to say, I have this n-dimensional data. I'm going to find an s-dimensional projection of it that tries to capture the directions in the data space that are most informative to the parameter. And now I'm going to introduce a further level of approximation, which is to condition only on ys and not just y. Okay? And so this is a priori reducing the dimension of the data. Why might you do this? Well, you know, in some sense, you could, you know, compress your data. There might be uninformative directions in the observation space. Many computational methods actually pay explicitly for the dimension of the data if you're trying to do amortized inference, where you essentially create a engine that will give you posterior samples for any realization of the data. Then you really need to parameterize things as a function of y. But this is also relevant to things like optimal experimental design, because optimal experimental design wants to find not necessarily the most informative projections of the data, but it wants to go one step further and find the most informative selections of the data. So imagine y is a vector that has like a lot of possible observations, but now I want to find sort of the most informative handful. I could essentially take what I'm going to describe as an eigenproblem and maybe go one step further and think about like a CUR decomposition or something that actually kind of, you know, a skeleton decomposition of the matrix that just picks out relevant columns. Okay, but let's just, you know, sort of set this up. So now I'm going to consider an approximation of the following format. I have my prior, and now I'm going to have this r-dimensional update of the prior in the parameter space, but I'm only going to condition on an s-dimensional projection of the data. So I'm really approximating in both senses. I'm updating the parameters only in r dimensions, and I'm projecting the data into s dimensions. And both s and r are smaller than the ambient direct dimensions of the parameter in the data. So I can take this expected KL divergence, and I can now decompose it into these two terms, where now I'm comparing the original mutual information of x and y with the mutual information of my r-dimensional projection of x and my s-dimensional projection of y. So now both of these projectors are sitting around. And I can decompose this further, and I can essentially say, okay, I can come to this inequality by saying I'm going to ignore this last term here. Since mutual information has to be non-negative, essentially I'm going to say, let me just take this inequality, get this inequality by focusing on these first two terms. But the nice thing is that this term is entirely a function of how I projected the data, or sorry, the parameters. And the second term is entirely a function of how I project the data. And now I could say, I could control the error on the left by controlling both of the two terms individually on the right. And so here I'm going to use essentially the same kind of machinery, except now we need a sort of more stringent assumption, was now, rather than just assuming that the prior satisfies a Lux level of inequality, Now I'm going to ask that the joint distribution of the parameters in the data satisfy an LSI. So this is a much bigger ask in some sense. But if I do that, then I can now project both the parameters and the data. And essentially I can construct an upper bound like this that involves two terms. And one term involves a parameter space diagnostic matrix, different than the one I had before. And the second term involves a data space diagnostic matrix, which is new. Now, these involve mixed second derivatives of the log likelihood, but the nice thing is that they're an expectation over the joint distribution of the parameters in the data. So this is a prior expectation, I want to emphasize. So this expectation is tractable because I can sample from the prior, I can sample y given x by running the forward model and evaluating the noise, and then these involve mixed derivatives of the forward model itself. So now the recipe is similar. I have this upper bound, and the upper bound is quadratic in this U-perp and this V-perp, and I can minimize it by solving eigenproblems. So that is kind of the story, with the caveat that we now need an LSI on the joint distribution rather than just the parameter part. Okay. Now let me give you an example of how this works. This is a test case that people have used in various CMC algorithms as a test case. It's a conditioned diffusion, but I want to emphasize what we're trying to learn here is essentially we have a particle that's essentially driven by Brownian motion in a double well potential that's given by this drift term here. But our goal is not to infer the drift. Our goal is to say, okay, I observe a trajectory of the particle with noise at specific times. And now I want to know what was the driving Brownian motion. So essentially I get to see a particle that's going to bounce around, and it might end up in this well or might end up in this other well over time. I observe one of these colored lines. And I want to know what was the sequence of, kicks, of Gaussian kicks that this thing experienced in order to get where it is. In principle, infinite dimensional problem, we can discretize things. And now let us look at what is the projection of the data that this machinery tells us to take. If I did something very naive, which is just to take the marginal covariance of the data and do principal component analysis, I would end up with these modes that tell me how to project the data. But if I minimize these conditional mutual information terms using or upper bounds for these terms using the LSI, then essentially the projections of the data that it tells me I should take are very much weighted towards being later in time, later in the trajectory. And intuitively, this kind of says observations near the sort of end time have more influence than observations in the early time. And that actually is useful because it sort of tells me observations later in time tell me kind of where, did I get more kicks to the upwards kicks or downwards kicks earlier in time? So somehow knowing where I ended up gives me more information in general about observing the particle position early on. It just sort of turns out that way. So this is the optimal projectors from the sense of minimizing an upper bound on the mutual information, say, look at where the particle ended up later on in time. So this is where it would end up in one well or the other. And this is borne out in essentially, looking at these mutual information terms and coming up with different ways. CMI is the method I described. PCA would be here. If you did canonical correlation analysis, you've got different projectors. But essentially, this is what we get, and here's the upper bound. Okay. So these kind of subspaces can help minimize posterior approximation error, both when you project the data and when you project the parameters. Okay. So this is sort of, a certain machinery. Under the hood, it all depends on either assuming that your prior satisfies an LSI, in which case you can do parameter dimension reduction, or that this joint distribution satisfies an LSI, which is a stronger assumption, but that lets you do parameter and observation dimension reduction. But now I want to kind of revisit that machinery and talk about some recent work that Matt and Olivier and I have been doing that kind of says, okay, could we do better than using essentially the kind of standard dimension-free log sublove inequality and do something that kind of more explicitly takes into account the dimension of the problem? Because I want to emphasize, we're dealing right now with finite dimensional inverse problems. The parameters x live in RD. But morally, maybe using the LSI is somehow not the best tool for dimension reduction because we have a finite dimension and we actually aim to reduce it. So, we don't sort of need this sort of dimension-free property of the LSI. Now there has, in the literature been kind of various dimensional versions of the LSI that have been proposed. Here is one, and it essentially looks like this. I'll kind of contrast it with the dimensionless LSI. So here again is the entropy, and essentially now the term on the right involves kind of a log det of this outer product of gradients, and it involves some moment terms as well. And I compare that to the original dimensionless LSI. Now, because of the log here, this can actually be exponentially sharper, but this does not tensorize. The dimension here appears explicitly. But this is an interesting inequality that we could actually now use in kind of similar sort of pattern of analysis and use this to try to find good subspaces. So what does that involve? This is kind of a new version of the same upper bound that I showed you at the beginning of the talk. Again, we're assuming standard Gaussian priors, some orthonormal matrix UR U perp, and I want to look at the error, the forward tail divergence between my original posterior and a posterior that is an R-dimensional update of the prior, where that R-dimensional update lives in the subspace spanned by the columns of UR. And this is the upper bound that we now get. Now, recall the previous upper bound was like essentially trace of a diagnostic matrix that involved the relative Fisher information. Now we have two terms. Now we have a term that involves essentially the second moment, or the uncentered covariance, posterior covariance, and the standard Fisher information. So log det of standard Fisher information. So this is grad log pi of the target, not just the likelihood. So not the relative Fisher information, the actual Fisher information. But what we've been able to show is that this actually uniformly improves over the previous error bound. For any UR that you pick in any D, this right-hand side is going to be smaller than what you got with our previous error bound. And it can be exponentially sharper. The other interesting thing that I want to point out is that when pi is Gaussian, unlike the previous result, this actually becomes equality. So the previous result was always an upper bound, even in the Gaussian case. There was slack, there was looseness in the bound. Now this actually becomes equality if everything is Gaussian, which is kind of reassuring. So somehow this says, we can, but what we thought was minimizing an upper bound can actually encode optimal dimension reduction in this Gaussian case. Okay. Outside of the Gaussian case, no, it's still just an upper bound. But that's kind of, suggests it might be more useful. So, okay. Now the program though is essentially the same. I have this thing, I have this, I suppose I can compute these matrices in some way. Now I want to minimize this thing over orthonormal matrices, or essentially sort of this Grassmannian manifold, sort of R, R unit vectors in RD. And now solving this is not a simple eigenproblem. So now we sort of have to resort to numerical methods, and we use Riemannian optimization methods. We use manifold optimization methods. The conjecture is that somehow this is benignly non-convex on this manifold. We're only able to, we always can try in many different places. We always converge to the same minimizer. It seems like there's only one minimizer, and it's a global minimizer, but we haven't been able to prove that. But numerically, in our experience so far, this seems like a relatively nice problem to solve. How well does it do? So in the linear Gaussian inverse problem, let us compare a couple things. So this is kind of a randomly generated linear Gaussian inverse problem. The global minimum value over all subspaces of this KL divergence. So this is the optimal R-dimensional approximation in black. What we got in our previous bound based on the dimension-free LSI was in blue. And then what we get with our new bound, except we need to use a certain number of samples to evaluate it. That's the number here, NS. 100 samples, the bound is the approximation is not as good. 200 samples, the approximation is better. But you can see this really achieves equality in the Gaussian case. So that's encouraging. How well does it do in a non-Gaussian case? So here's an example that I think is kind of neat. I have this target distribution that's this banana-shaped thing on the left. And I want to approximate this distribution as a one-dimensional update of a standard Gaussian. And so I'm looking for the optimal subspace, but essentially means I just need to pick an angle, because all subspaces are parameterized by an angle. If I minimize our previous upper bound, it tells me that it tells me that UR points in this direction. It says update things in this direction. And if I minimize the new upper bound, then I get the red arrow. It says, update the standard Gaussian reference distribution in this direction. Now, what does the best approximation look like when I update in the orange direction? Well, it looks like this. And what does the best approximation of this two-dimensional target look like when I update in the one direction given by the red arrow? Well, it looks like this. Now, visually, I think the thing on the right seems better than the thing in the middle, but you can see this quantitatively. Here I'm basically showing for different choices of angles, so basically different choices of subspace, the KL divergence between pi and its best one-dimensional approximation given that subspace, and the dimension-free bound, I call the CDR bound, certified dimension reduction, actually says that the bound is minimized here. So it would have told me to pick this orange direction here, which corresponds to this arrow. The new bound is given by the blue, and it says, and so minimizing the bound would give me this direction. And it's almost, but not quite equal to the optimal direction. Optimal direction is, close by. So, in general, I don't know that this is always the case, but in this example, minimizing the bound given by the dimensional LSI actually gives you much better performance. And in some sense, actually, the bound given by the dimension-free LSI is almost the worst subspace you could have picked. The worst subspace is probably right around here. So this works quite a bit better. Some further intuition. So just to kind of give you some intuition for what this dimensional LSI encodes. Here's an example I find to be quite illuminating. Instead of setting the reference to be a standard Gaussian, let the reference row be the best Gaussian approximation of pi in the sense of minimizing this forward KL divergence. So suppose, let me take mu to be Gaussian, let me minimize this thing, and what I will find is that mu matches the moments of pi, the first and second moments of pi. So the best Gaussian approximation in the forward KL sense is always the moment matching approximation. And so let me pick that to be my reference. So I'm going to set rho to be essentially the Gaussian with mean m pi and covariance c pi. And now let me find a subspace that best captures departure of pi from its best Gaussian approximation. If I plug all that in to the previous machinery, essentially what we end up with is this. So if rho is the best Gaussian approximation, and UR is the subspace that is a candidate subspace that I'm going to use to look at the departure from this best Gaussian approximation, I end up with this upper bound. And this upper bound depends on, here I'm parameterizing it by UR, but I'm parameterizing it through this WR, through the simple transformation. And this upper bound is something I can minimize tractably by solving an eigenproblem. So this thing, I can minimize it by basically choosing WR to be the leading generalized eigenvectors of this matrix tensor. Now, what is this thing? This is the Fisher information of the target, and this is the inverse covariance of the best Gaussian approximation. So the precision of the best Gaussian approximation. And the resulting error bound now is given exactly by the sum of the trailing generalized eigenvalues. But there's a lot of intuition here, because if pi were actually Gaussian, this Fisher information would be, so I think I'm missing an inverse here, but basically, yeah, I'm missing an inverse here. It would be basically c pi inverse. And then all the eigenvalues would be 1. So insofar as these things disagree with each other, this is a capturing departure from that Gaussian approximation. And that's precisely what then the subspace that we find tries to target. So, okay, maybe the final example I want to give you is just kind of a fun example where now we have this is actually a example motivated by some collaboration with people in industry where they're doing essentially trying to image the subsurface. And there's a lot of interest in coming up with very fancy priors for imaging the subsurface, in particular coming up with priors that are based on generative models. So here, offline people developed essentially a generative adversarial network, sort of generative model for the prior, which takes a Gaussian prior and then pushes it forward through some sort of decoder that gives you images of the subsurface. So here I have this latent Gaussian, this 300-dimensional, I have this decoder, and these are images of possible subsurface structure that I get. Now, this already encodes a lot of dimension reduction. So someone that said, okay, this 300-dimensional latent space is to be able to give me images that have plausible geological structure. And so I've already done a lot of a priori dimension reduction. But now the inverse problem essentially transfers to one of now conditioned on data, tell me the posterior distribution over this latent space Z. So I could really think about this as a problem with a Gaussian prior and a complicated forward model, because this encoder, or this decoder, the GAN, really becomes part of the forward model. So essentially, I have a prior on Z, standard Gaussian. I have a forward model that represents the measurements composed with the GAN itself. So that's my kind of combined forward model. If I apply this machinery, then basically, you can still find a lot of opportunity for dimension reduction that goes beyond the latent dimension of the prior. So basically, this is the upper bound on the error that we get by applying our machinery. And it says there's basically further dimension reduction to be had in this latent space Z when you take into account the forward model and thus the likelihood. And here's sort of an example you would get for the full dimensional Z. And this is what you would get with sort of different R-dimensional projections of Z. And you can see there's differences here, but somehow the difference between the left panel and these panels really accounts for what is informed by the data and what is not informed by the data. So this dimension reduction is really trying to focus on take out only the things that are going to be informed by the data and worry about those. Everything else can be sampled from the prior. So with that, I think we're coming up on time, so I'll try to conclude. If there's one take-home message, it's essentially that by using, essentially LSIs and different versions of LSI, we can identify subspaces of the model parameters that are informed and subspaces of the data that are informative. And then this essentially reduces the dimension of problems in different ways and enables algorithms for sampling and high dimensional inference. A lot of things that I think will be interesting to do in next steps. One thing I should say is, we essentially form these very general diagnostic matrices, and all the potential for dimension reduction is encoded in does the spectrum of these diagnostic matrices decay quickly. What would be very interesting is to now start to say things about specific PDEs and specific observation setups, and then you could say something about how actually using the structure of those PDEs to say specific things about the diagnostic matrices that you would get. Another really interesting line of extension, which I have to say Giuseppe Carreri and Han Jing Li have a very interesting paper that came out this fall, which is to extend these dimension reduction method notions to the infinite dimensional setting, where you're really trying to learn functions rather than discretized functions or parameters that live in RD. I don't think this is particularly trivial, but this nice paper that came out in the fall actually takes the linear dimension reduction that I talked about at the very, very beginning of the talk and formalizes that in the infinite dimensional setting. And so that was already a lot of work, but it's a nice paper to read. But one could imagine trying to do the same thing now for nonlinear problems. Quantifying the impact of a dimension reduction on sampling efficiency. So here in this talk, I didn't get into this, but I kind of took for granted that if you could reduce dimension, MCMC will be faster, variational inference will be faster, and all these things, which certainly believe to be true, and it's been true in our experience. But actually quantifying that would be relevant. And maybe the final thing I'll mention is that all the dimension reduction that we've done, even if you're handling a nonlinear problem, certainly the forward model is nonlinear, all these kinds of things, is linear dimension reduction. So we've been talking about linear dimension reduction, finding subspaces for nonlinear problems. Very natural to now consider, could I consider nonlinear notions of dimension reduction, maybe using autoencoders or something like that. And we're thinking a bit about, in those lines as well. So I'll thank you for your attention. I'll put up a couple of papers in case you're interested, and I'd be happy to take any questions that you might have.
Great. Thanks so much for a very nice talk, Youssef. So it's a very relevant, interesting problems. So if you have questions, please unmute yourself and ask questions.
Hi, Youssef. I have some easy basic questions. I didn't follow quite. So what is UR for most situations? Is the SVD of the Jacobian of the dynamics or the SVD of the transportation matrix? I didn't follow. Could you say it again?
UR is the leading R eigenvectors of an SPD matrix. So for instance, the leading R eigenvectors of this thing.
So what's the dimension of this matrix?
So this is D by D, where the parameters X are D-dimensional.
And
so
D is
UR is basically a D by R matrix with orthonormal columns.
I see. And D is the dimension of which
of the parameters that I'm trying to learn. So
okay.
like so when I set up the inverse problem, say like here, X is d-dimensional. And the diagnostic matrix that I construct is going to be d by d. And then I want to find the leading R eigendirections in that matrix.
And and solving for the SVD is roughly cost to solving how many forward problems? Is that a comparable thing?
Well, it depends on the rank. I mean, so it really, you just want the leading eigendirections. So it really depends on the decay. I mean, we typically use some kind of like randomized SVD or something like that.
I mean, related, I assume you know the rank. Like what's the, actually,
Well,
for
yeah,
a
I mean,
given
so,
R.
sorry?
For a given R, like if you're showing U is D multiplies R matrix, then how many forward solve would that be equivalent to? Is that a reasonable question to ask?
Yeah, I mean, so the whole thing is sort of order, I guess d over yeah, whatever it's sort of order dr squared. But basically, like we want to kind of do R is not typically set a priori.
Yeah.
What we want to do is say, okay, I have a certain, maybe you have a computational budget that allows you a certain R, but essentially it's kind of a problem of like probing the rank of this matrix or trying to find some, you want to get a sense of how quickly the spectrum of this matrix decays. So here, for instance, here, the spectrum decays very quickly. And so I really only care about finding like the leading R eigendirections of this thing. And so I would use, so in practice, we use some kind of matrix tree method and just apply this.
Okay, thanks. Yeah, thanks for the talk.
But I don't know if that's clear. I'm happy to ask more questions if that's not clear. So yeah, so this is, insofar as you can come up with, numerical methods can take advantage of the low rank structure. I mean, there's sort of a bit of chicken and egg. If the problem has low dimensional structure, then finding the leading R eigendirections of this diagnostic matrix is cheap, and they will give you a good approximation. If the problem has very little low dimensional structure, then the problem is just hard according to these methods, and you'll have to work hard to find the eigenvectors, but they also won't give you a particularly good approximation unless you take a lot of them. So it's kind of a self-fulfilling thing. So that's why I like to think about the matrices not as like that's why I like to think of the matrices as a diagnostic, because they tell you whether the problem you have that you're facing can be well approximated in the format that we're considering.
I see. And also when you try to reduce the, you first reduce the parameter space, you also reduce the data space. The data space, you use the same rank as when you reduce the...
That's a great question. Not necessarily. Only in the linear Gaussian setting. So in the linear Gaussian setting is nice. The eigenvalues of the data space pencil and the parameter space pencil are exactly the same. Outside of the linear Gaussian setting, you might have different projections. You might have a higher rank for the data and a lower rank for the parameters and vice versa. You don't know. Essentially, these two matrices that I'll show you here could have different spectra in the non-Gaussian setting.
Okay, yeah. I see.
Why? Because I mean, it looks like, okay, this is like a flipped around version of that, but these are averaged over X and Y. And it turns out then these can have, in general, rather different spectrum.
Okay.
Any other questions for Youssef? I was just wondering, also you mentioned a nonlinear dimension reduction towards the end. So then you mean a nonlinear mapping of dx, or and then there will sort of a trade-off in between dimension, I guess, and the nonlinearity.
Exactly. Yeah. Imagine like so here's a kind of contrived example. Imagine you have a particle whose distance from the origin you observe, and so I have a prior on the position, but all I get to observe is the distance from the origin. So somehow the informed direction is here, and the uninformed direction is like at this azimuth, or conversely, I observe the angle, but I don't observe the distance. So if you apply So the posterior would be, for instance, like living on a ring, if you only observe the distance. If you apply linear dimension reduction, then it says, okay, there's nothing you can do. Like everything is equally important in R2. But nonlinear dimension reduction could say, no, there's actually some sort of like, foliation of the space into like uninformed and informed manifolds. And that it's much more delicate, like how can you construct such a thing? Certainly more expensive. So then indeed, I think there is a trade-off between letting yourself be nonlinear ought to offer the possibility of a smaller R, but the machinery will be much more complicated.
Yeah.
And so that's exactly the trade-off.
Great. Thanks. Well, it's very nice talk. So if there are no other questions, we'll thank the speaker once again. It seems to be quite important techniques, and I really liked the talk. So thanks so much.